Now it is chapter 7, feature extraction, data compression. There are two main categories of dimensionality reduction methods. One is feature selection, and the other one is feature extraction. Through feature extraction, we may construct a new feature subspace. In practice, feature extraction is used to improve storage space or to improve the computational efficiency. However, more importantly, it is used to improve the predictive performance. In this chapter, we'll study three fundamental techniques for dimensionality reduction: principal component analysis, PCA, linear discriminant analysis, LDA, and kernel principal component analysis. And of course, we'll study singular value decomposition as well. Let's go to section 7.1, principal component analysis, PCA. The PCA is a statistical method that uses an orthogonal transformation to convert a set of observations to a set of linearly uncorrelated variables called the principal components. The orthogonal axis of new subspace can be interpreted as the directions of maximum variance. For example, for this data set, the maximum variance, the direction is this one, so that the first principal component will have this direction. We'll see details very soon. The PCA is an unsupervised technique because we don't use labels. The PCA can identify patterns in data based on the correlation between features. Here we have a warning. The PCA directions are highly sensitive to data scaling, and we need to standardize the features before using the PCA. Okay, here we have how to compute principal components. The data metric X is in n by d dimensions. Each row represents a data point, and each column gives a feature. And we assume that each column has zero mean after standardization. In PCA, the goal is to find an orthogonal range metric or orthogonal transformation metric W in d by d dimensions such that the transformed metric maximizes the variance. That means that we'll try to find vectors in this range metric so that try to extract a maximum variance for each weight vector, so that later the reconstruction error must be minimized. Here, the transformed matrix Z is called the score metric, and each column of Z represents a principal component of the data metric X. Now here, we start with how to find the first column of W. So it's W1. Now here, X, and we have weight vector W1, then it'll give a vector Z1. Now we'll try to maximize Z1, and we'll try to find the W1 such that this multiplication is maximized. That is a mathematical formulation. Here, of course, in W1, norm of W1 must be 1, so that here maximizing xw norm squared with w norm is 1. That is a mathematical formulation, and the w which maximizes that xw norm squared is called the w1. Now this one can be written in this way, and then rather than norm is 1, just non-zero w and divide by norm squared, so that they are the same equivalent problem. Such term is called Rayleigh quotient. For the maximizing Rayleigh quotient, we have really good theory in numerical linear algebra. For positive semi-definite metric, such as x transpose x, the maximum of the Rayleigh quotient is the same as the largest eigenvalue of the metric, which occurs when W is the corresponding eigenvector. That means that here W must be the eigenvector corresponding to the largest eigenvalue, and this maximum value at the moment, the maximum value must be the largest eigenvalue. So here W1 can be here found in this way. W1 just normalized. Here the V1 is the eigenvector corresponding to the largest eigenvalue. Now this theorem gives how to find the first column of the Wayne matrix. However, for the other columns, so that W2 and W3 and so on, here we assume that the first k-1 weight vectors are found. Then to find the WK, here we do in this way. Subtract the first k-1 principal components from x. So the mathematical formula is given in this way. Try to subtract the k-1 principal components from x. Then we say that is xk hat. Now, from this new matrix, we try to extract the maximum variance. So here, now, the weight vector W is multiplied, and we want to find the W such that this one is maximized. The maximizer is called WK. In this way, recursively, we try to find the WK. Now, for this mathematical problem, it turns out to give some very simple solution. It gives the remaining normalized eigenvectors of x transpose x, so that the transformation matrix W is the stack of eigenvectors of x transpose x. Here W is the stack of eigenvectors, W1 to WD. Now here, but these are just correspond to the decreasing the eigen values, so that W1 is the corresponding eigenvector of the largest eigenvalue, and W2 is the eigenvector of second largest eigenvalue, and so on. Now it's normalized. So W can be found in this way. Okay. Now, once W is found, then for given theta vectored x, and here the transform is transformed to d-dimensional row vector of principal components. So one row in the theta set will make one row in the square matrix. here, from singular value decomposition, we can understand this one. The weight matrix W in D by D dimensions is the collection of eigenvectors of X transpose X. Now, the score matrix Z is the stack of eigenvectors of X transpose. Don't be confused. W is the collection of eigenvectors of X transpose X, that one. And Z is now eigenvectors of X transpose, okay? And now scaled by square root of eigenvalues. So here, X transpose X has eigenvectors now uj and normalized, and then now scaled by here now lambda j and square root of lambda j, so that these are just scaled eigenvectors of X transpose. Okay, here X transpose X and now lambda j is eigenvalues of X transpose X. This lambda j also the eigenvalues of X transpose. Okay. Okay, this is how to find weight matrix. Okay, now we'll continue in the second part of the section. Thank you.